So we're literally swimming in data every single day, right? But have you ever stopped to think about where it actually comes from, like for real? And maybe the bigger question is, can we even trust it? Well, that's what we're going to dive into. What it really takes to build an architecture of trust for our digital world. And look, this isn't some abstract philosophical question. It's super practical. You're dealing with data-driven systems all the time, every single day. Being able to tell if what you're seeing is legit, if it's been tampered with, or if it's just completely made up by an AI, that is hands down one of the biggest challenges we're staring down in tech right now. I mean, with generative AI, making fake stuff is ridiculously easy now, and that creates these huge problems. Think about something like data poisoning. You could have a self-driving car's AI being trained on fake images. That's terrifying, right? Or what about the Oracle problem? That's where a totally secure smart contract gets fed bad, unverified data from the outside world and acts on it. This stuff isn't just a simple bug, you know? It's a fundamental risk to the entire digital world we've built.
Okay, so how in the world do we fix this mess? Well, there's no silver bullet here, no one magic tool that solves everything. The real answer is a complete structured way to verify our data. It's a whole framework, and we call it digital provenance. Let's get into it.
So, to really get a handle on where our data comes from, we have to look at it from three different angles. And the solution is this really cool holistic model called the provenance triad. It breaks everything down into three key parts: content, context, and execution. Let's break down each one. All right, first up, content provenance. This is the what. The easiest way to think about this is like a digital fingerprint for your data. It uses some clever cryptography to prove that a file has not been changed. I mean, not even by a single bit. It's the absolute foundation of trust. It answers the simple question, is this file exactly what it's supposed to be? But a fingerprint alone isn't enough, right? So next, we need context provenance. This is the who and why. A digital fingerprint is kind of useless without the story behind it. Context gives us that story. It tells us who made the data, who approved it, and why they did it. This is the part that's actually readable by humans, the audit trail that lawyers and compliance officers really care about. And the third piece of our puzzle is execution provenance. This is all about the how. Now, if you're in science or you're a developer, this is absolutely crucial. It's the technical history. It tells you the exact code that was run, the specific software versions, the whole environment that was used to generate or change the data. If you don't have this, you can't reproduce a result. And if you can't reproduce it, you can't trust it. It's that simple. It's key for both science and, just basic debugging. So let's put it all together in one place. You can see how these three dimensions work together. For content, we're worried about integrity, and our main tool is cryptographic hashing. For context, we need attribution, and that's where standards like W3C PROV come in. And for execution, it's all about reproducibility, using things like open Lineage or an SBOM. When you combine them, bam, you get a complete, verifiable history of any digital asset. All right, let's move on and pop open the Provenance Toolbox. We're going to look at the actual semantic and cryptographic tools that make this whole architecture of trust a reality. Okay, so the foundation for that whole context layer we talked about is a standard called W3C PROV. The best way to think of it is like a universal grammar for Lineage. It's the language we use to tell the story of our data. And because it's a standard, it means different systems can all speak the same language. One system can write a provenance record and another one can read it and understand it perfectly. Super important. And this grammar is actually built on three really simple ideas. You've got an entity, which is the what, like a CSV file. Then you have an activity, which is the how, say a script that's running. And finally, you have an agent, which is the who. That could be a person or maybe a server doing the work. That's it. Pretty much anything you need to describe about a data's history can be built using just those three simple blocks. Okay, let's switch gears to the crypto side of the toolbox. Now, it is super easy to get hashing and digital signatures confused, but they do very different jobs. Hashing proves integrity. It gives you that unique fingerprint and answers the question, has this data changed? A digital signature, on the other hand, proves authenticity. It's like a verifiable lock that answers, did this specific person approve it? And here's the key. You absolutely, positively need both. So that sounds great. But what happens when you're not dealing with one file, but millions of them? Signing every single one would be insanely slow and expensive. And that is exactly where Merkle Trees come in to save the day. They're this brilliant cryptographic structure that takes all the hashes from all those records
and combines them into one single tiny root hash. It's an efficiency engine. It makes it possible to secure data at a massive scale without grinding everything to a halt. Now, how do we make sure that root hash is set in stone and can't be changed? Well, to get an unbreakable, immutable timestamp, we use a technique called blockchain anchoring. What you do is take that hash, like a Merkle root, and you stick it inside a transaction on a public blockchain like Bitcoin or Ethereum. In doing that, you're basically using that huge, global, decentralized network as a public notary. The result is a permanent tamper-proof timestamp that proves beyond a shadow of a doubt that your data existed in that exact state at that exact moment in time. Okay, we've covered a lot of ground. We've got the core concepts, we've looked at the tools in the toolbox. Now for the really important part, from code to compliance. How do we actually take all this theory and put it into practice in real-world systems? So, a really practical system designed for this uses a 3-layer architecture. First, you have layer 1, the asset store. This is just where your files actually live. Think of a data lake or something similar. Then you've got layer 2, the provenance graph. This is where the semantic story lives, the W3C PROV stuff, which makes it super fast to query. And finally, layer 3 is the immutable log. This is where you put your cryptographic proofs, like your hashes, anchored on a blockchain. It separates the story from the proof, which is really. Okay, but wait a second. This brings up a really, really big question. An immutable log is fantastic for security, but what about privacy laws? I'm talking about things like GDPR and the right to erasure. If your proof is permanently stuck on a blockchain, how can you possibly delete someone's data? You can't just go back and edit the chain. And here's the brilliant, elegant solution. It's a pattern called crypto shredding. Here's how it works. Step 1, you don't store the personal data in the log. Instead, you hash it with a unique, secret key called a salt. Step 2, you secure that salt in a totally separate, normal database that you can edit. Now, step 3, if a user asks you to delete their data, you don't even touch the blockchain. You just shred the salt. And without that salt, the hash in the log is just random noise. It's gibberish. You've permanently broken the link to the personal data while keeping your immutable log perfectly intact. It's pretty genius. So, when you bring all of these pieces together, the architecture, the crypto, the privacy patterns, you can start to enforce a really powerful policy. And that policy is no provenance, no production. Just think about what that means. It means your automated systems, like your CI/CD pipeline for deploying software, would just flat out refuse to push any code or use any data that doesn't have a complete, verifiable chain of custody. It's trust, automated. Now, let's be realistic. You don't just flip a switch and have this overnight. Implementing this is a journey, and you do it in phases. You'd probably start in the first few months with just getting visibility, deploying agents to see how data is flowing. Then, you move on to integrity and control, putting hashing and digital signatures in place. After that, you'd work on immutability by connecting to a blockchain. And finally, the last step is interoperability, enabling others outside your organization to verify your assets. And this whole process is really about moving up the maturity model. You start out in an ad hoc state, where you've just got scattered logs everywhere, which is super high risk. Then you get to a managed state with centralized logs and some semantic lineage. But the goal, the target state, is to be optimized, where your trust is completely automated with cryptographic anchoring. You get to a point where you don't need people doing manual checks anymore because the system guarantees it. So, what is the #1 thing to take away from all of this? It's that digital provenance isn't just one tool or one idea. It is a single, unified architecture that secures the entire data lifecycle. It beautifully weaves together the semantic story of data, the mathematical certainty of cryptography, and the real-world rules of governance. And really, what this all comes down to is a fundamental shift in our mindset. For too long, we've been reactive, right? We wait for a data breach or a model to fail, and then we scramble to figure out what went wrong. Digital provenance is about getting proactive. It's about building a future where our data is trustworthy by design. It's born trustworthy and stays that way its entire life. So that leaves us with one last big question to chew on. As you're thinking about your own futures in tech, ask yourself this: is no provenance, no production the future of software development? Are we heading toward a world where shipping code or deploying an AI model without a verifiable, trustworthy chain of custody is seen as, well, professional malpractice? Is this what it's going to take to build software responsibly? Food for thought.